Okay. Oops. Okay. So, rational functions. Oh, I meant to put blanks in this one too, and I've done it all wrong. All right. Rational functions have zeros. Any value where the numerator, that was supposed to be a blank, that's why there's funny spacing, equals 0, but the denominator does not equal 0. Okay? Why can the denominator not equal 0? What happens if you try to type something like 7 divided by 0 into your calculator? Error, right? You cannot divide by 0. So, if you are getting a 0 in the denominator, it is going to cause some issues. And actually, we're going to talk more about that in the notes that we're going to do today, what kind of issues it's going to cause. It's going to cause holes or vertical asymptotes in our graph. Right now, all we need to think about for this part is we know we cannot have zeros in the denominator. But if you're asking for zeros of the function, you do want the numerator to equal 0. So we cannot have a situation where we got like something divided by 0. That can't happen. But we do want to have 0 over some number, right? That's what we want to have. Because if we do 0 divided by 10, or 0 divided by -5, or 0 divided by anything besides 0, we will get 0 for our answer, and that is what a 0 is. It's where your output value is 0. So, what you're going to do for these problems, if it says find all zeros of the function and you're dealing with a rational function, you want to go ahead and if it's not already factored, you want to factor for that. Factoring, as you can see, we've done this lots of factoring, so it's not going to go away. To factor that top x squared, we need to have an x here and an x here. We need numbers that multiply to give us 3 and add or subtract to give us 4. What numbers would those be here? 3 and 1, both of them positive, right? So plus 3 plus 1. 3 times 1 is 3. 3 plus 1 is 4. That works perfectly. Okay, that factors the top. On the bottom, we'll have an x and an x. This is a special case, right, where we're missing the middle term, which means we need to multiply to get 9. What do we need to add to get? Add to get 0. To get 0 there because that middle term's missing, right? So what numbers could I use for that? Plus 3 and minus 3. Okay, so once you do this, you cannot have zeros in the denominator, right? That means, I'm going to write this, x cannot equal -3, and x cannot equal +3. Right? So in that denominator, x cannot equal -3 and x cannot equal 3. So what's going to happen is if I get answers that are 3 or -3, I've got to throw them out, right? So now if I look at the numerator, which is where I'm going to find my zeros, right, I would get x equals -3 from this first one, and I will get x equals -1 from the second one. But what's our problem? Can't use -3. So although it would give us a 0 in the top, it also gives us a 0 in the bottom, so it's not a 0 of the function, right? So we're just going to have x equals -1 is our 0. And that means we got an x-intercept at -1, 0. Right? We got an x-intercept at x equals 1. Okay, not too bad. We can do that. All right. It really all mostly relies on you to being able to factor, right? I purposely threw in here, for example, 2, one that's a little harder to factor because I have noticed that we definitely have a little trouble factoring when we got that number in front of our x right there, all right? For this one, we need 2 sets of parentheses, and this time, we got to multiply to get 3x squared. To do that, we're going to have to use 3x times x. So 3x and x, or you could switch the order. It doesn't matter. All right. And then I've got to multiply to get positive 4, which to get positive 4, I could use 2 times 2. I could use negative 2 times negative 2. I could use 1 times 4, or I could use negative 1 times negative 4. All right, do I want to use positives or negatives for this one? Negatives, or else I won't be able to get that negative there in the middle, right? So this one's out, this one's out. It's got to be the negatives. Now, do either one of those add to give us negative 7? They do not. And even if they did, they still might not be the answer, because these are the ones we got to guess and check on, right? So I'm just going to have to pick one and try it. I'm going to try negative 2 and negative 2. I like picking the ones that are closest to each other first. Seems like they work more often, but maybe not. So if I do this, now I've got to multiply back to check. So 3 times x is, I'm going to write over here to the side, 3x squared. 3x times negative 2 is negative 6x. Negative 2 times x is negative 2x. And negative 2 times negative 2 is positive 4. Does that give us negative 7 in the middle? It does not. This is not the right answer. Normally, I would switch where they're at. Is it going to matter if I switch where they're at since they're the same number here? No. So it's got to be 1 and 4. So let's try that. Minus 1 minus 4. Let's try and see if this will work. So we got to multiply again. 3x times x is 3x squared. We know that. Really, it's the middle terms that we got to check. 3x times negative 4 is negative 12x. It's not looking good. Minus 1x plus 4. Does that work? No. So hopefully, when we switch the 1 and the 4, it's going to work. Because if not, we don't have anything else to try. So if I put the 4 here and the 1 here, now when I multiply back, I get 3x squared minus 3x minus 4x plus 4. Does that one work? Yes, finally. So we have the one that works there. Those are a little hateful, but you just got to kind of guess and check with those there. What about my denominator? How do I factor that? It is missing a term, but this time it's missing the last term. So if I tried to like multiply to get a 0, it's going to be kind of weird. You can do it that way, but there's an easier way to do it if it's the last term that you're missing. You can use 5 and 0 or 2 and 0, but this has 2 x's, this has 1 x. We can just pull out a greatest common factor, right? They both have x's, so we can take an x out, and then we'll have 2x minus 5 left inside of the parentheses. So if it's the last term you're missing, if all of your terms have x's, you can pull an x out. Sometimes you can pull a number out too, but we can't on this one. There's no number that will go into 2 and 5. So part of this is just remembering how to factor all this stuff that you used to know how to do, but it's probably a little bit iffy now, right? So we're going to look at our denominator first, because we got to know what our excluded values are, the things that cannot happen. X cannot equal 0. 2x minus 5, what number can we not equal there? Nope. 5 halves. Because we got to do, for that one, Lucas, we got to do 2x minus 5 equals 0, so we got to have that 2 right there. We'll move the 5 over, so we'll get 2x equals 5, and we got to divide by 2. So if you have a number in front here, it can't just be the opposite sign. You got to solve that out, and we'll get x. Actually, this cannot equal 5 halves. So we can't have 0, we can't have 5 halves. However, let's look at the top to see what numbers we're getting. Let's do this one first because it's easier. X minus 1 is going to give me x equals positive 1. 3x minus 4, it is going to be 4/3. in numerator and denominator, you're looking for the denominator would equal 0, and it cannot equal 0, right? So, like, essentially, you're setting this one equal to 0 and this one equal to 0 here, or really not equal because it's in the bottom, can't equal. Then you're doing the top equal to 0 and this one equal to 0. Everything's equal to 0 in the top, everything's not equal to 0 in the bottom. And so, like, for the more simple ones, like x minus 1 equals 0, you could write it out like that if you want, but it's just the opposite sign of whatever you have in the parentheses. But one like 3x minus 4, I'm going to do this up here, 3x minus 4 equals 0, you're going to add that 4 over to the other side, so 3x will equal 4, and then you still have that 3 in front, so you got to divide by 3. So x would equal 4/3. Now, are 1 or 4/3 or either one of those excluded values? They are not. It's 0 and 5/2, so both of these are answers. To kind of shortcut it, you'll notice, like if you have the same factor on the top and the bottom, that's going to end up being an excluded value, and it's not going to count as a 0. Over here, because we didn't have that happen, just the numerator, both of the numerators are going to work for that. Okay, questions? Okay, so numerator is equal to 0, denominator is not equal to 0. That's what you're looking for on rational functions. All right, let's look a step further. Okay, and we need to solve some rational inequalities. These are going to be a lot like the polynomial inequalities. We're going to use that chart for it. The first thing that we want to do is we want to find all zeros and excluded values for the function. So zeros are in the top, excluded values are in the bottom, right? I'm going to put us a little note right here. This comes from the top, and this comes from the bottom. Right? So this one is already factored for us, so we do not have to factor like we did on the others. We're just going to take each piece and set it equal to 0. So like here I'll have negative 2x squared equal to 0. I could divide by negative 2. I'll still have 0. Square root both sides, I'll still get 0. That's just going to be x equals 0. 0 is the only number that will make that 0. This is going to be x equals positive 1. This is going to be x equals negative 2. And then in the bottom, x cannot equal 5. That not equal actually ends up not being all that important. For this, 5 is important. We're going to need to use it. The fact that it does not equal is not all that important because is this question asking us where we're less than or equal to 0 anyway? There's no or equal to, so this is not going to be too critical that that's a not equal instead of equal. On the next problem, it's going to matter a little bit more. So what we're going to do for this is we are going to make a chart just like we did with polynomials. And we're going to put all of these zeros and excluded values on our line. So we are going to put them in order. So we would have negative 2, and then 0, 1, and 5. Include the excluded values here as well. If you want, sometimes I like to put an X right there on that 5 just to remind me it can't be equal to 5. But yet it's still going to be a boundary point that we want to look at. And then we are going to, like we did on our polynomial problems, we're going to take each piece, top and bottom, and put it over here on the side. So I'm going to have negative 2x squared. I'm going to have x minus 1. I'm going to have x plus 2. And I'm going to have x minus 5. And then I'll put my answer down here at the bottom. It doesn't matter whether those numbers come from the top or the bottom, they still get included in your chart. And so if we look at our chart, we're going to do just like we did with polynomials. We're going to go across. X squared is always positive. But what happens when you multiply it by negative 2? It goes back to negative. So you're going to get negatives all the way across on that one. Okay, for x minus 1, anything lower, like negative 3, that's going to give you a negative. You'll get negatives all the way until you get numbers bigger than 1. Like 2 would be positive over here, so that one will switch right here. For x plus 2, anything below negative 2 is going to give us a negative. But then anything bigger than negative 2, like negative 1 or 0 or whatever, is going to give us a positive. So we'll fill in that chart. And then for the last one, x minus 5, we will have negative, 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 positive. And so when you're looking at your chart, if you think about what's happening here for this section, you're doing negative times negative times negative. Those three on the top multiply together, right? That gives you a negative in the top. And then you divide it by a negative, and it makes it positive, right? What happens here is it ends up being the same as the polynomials. If you have an even number of negatives, then you're going to get a positive down here. So we got 4 negatives, that's even, we get a positive. It really doesn't matter whether you're multiplying the number 4 times or whether you're multiplying and dividing, because the rules are the same for multiplying and dividing. If you got the same sign, it's going to be positive, different, negative. So it really doesn't matter that my x minus 5 is in the bottom for that. And then we'll get a negative here because we have an odd number of negatives. We still get a negative here, right, because we have an odd number of negatives. We get a positive here, negative here. Okay. Now, we've got less than 0. Is this question looking for the positives or the negatives? Negatives. So we got negative here, negative here, negative here. Now, this is a less than problem. It's not less than or equal to. So it is almost true that from negative 2 all the way up to 1, you get this answer. Except at 0, it's equal to 0. So we want to list these two sections separately. We want to do negative 2 to 0, and then 0 to 1. And we're using parentheses because it was a less than problem. So we don't want to include those endpoints. And then we also have 5 to infinity. On this problem, it does not matter that I put that x on that 5 because I'm using parentheses anyway because it was a less than problem. If that was a less than or equal to, we'll see it on the next problem, it would matter a little bit more. Okay, so this will be our answer. Usually when I teach these, we haven't done the polynomials first. I think the polynomials make this so much easier. You've already seen it some there. Okay, let's do one more for that. Okay, this one's not factored. I, on purpose, put us a harder one to factor there again. So factor that out for me. I'm going to give you a second to think about it on your own. Alright, check with your neighbor and see if they've got it factored right. See, several of you that have it factored correctly, and some of you that are still working on it. Check with your neighbor and see what they got. So on that factoring, I know 2x and x have to be my numbers that go here because that multiplied together would give me the 2x squared. Sometimes there's more options. Like if that was a 4x squared, it could be 2x and 2x or 4x and 1x. Thankfully, there's only one option right here. What can I multiply together to get negative 7? 7 and 1. One of them needs to be negative, right? Or I could do negative 7, positive 1. Those are my only options, right? So there's not a lot of options to test here. But if I check, like, plus 7 minus 1. What I usually do when I did this, I usually do these in my head. So, like, what we would be working towards, like, best case scenario, you can do these in your head. But what I'm doing in my head is I'm looking at this and I'm thinking, what do I get here? And what do I get here, right? The first and the last should be correct because I picked 2x and x to get x squared. I picked positive 7, negative 1 to get negative 7. So those should be correct. So really I just need to check the inners and the outers. And so this will be 7x and this will be negative 2x. And that does not give me positive 13, right? So that does not work. I am going to need to change where these are at here. So let's make this a plus 1 minus 7. And then again, I usually do this in my head, but you certainly can write it out. You'll get 1x here, and you'll get negative 14x here, which gives me negative 13x if I add them together. Is that correct? No, but it's really close this time, right? I just have my signs wrong. So if I change this and make it negative and make this one positive, then I'll get a negative 1x, a positive 14x, and a positive 13x for that. So you just kind of got to play around with it until you get it to work. So it should factor into this right here. That's what we should be looking at. If your x plus 7 is first instead of your 2x minus 1, that's perfectly okay. So we are going to get the zeros for each one of these. So for this one, we got 2x minus 1 equals 0. That is 2x equals positive 1. Divide by 2. X equals 1/2. There's one of my zeros. I'm also going to have x plus 7 will give me x equals negative 7. What do I get for the 3 minus x? It's a positive 3. Right, be careful with that. Sometimes people want to use a negative 3. When you got 3 minus x equals 0, I just usually take that x and add it over to the other side. 3 equals x. So we've got 1/2, negative 7, and 3. And actually, what should I have used on that 3? Can x equal 3? It's in the bottom, so I'm going to put it does not equal. And it is going to matter on this because of that or equal to sign with that 0. I'll show you. It's just a tiny little difference, but I'll show you what it looks like here at the end. So we're going to put these on the number line, and we'll have negative 7, 1/2, and 3, and we will put 2x minus 1, x plus 7, and 3 minus x over here on the side, and then a place for our answer. Okay, so for 2x minus 1, if I plug in something like negative 8, 2 times negative 8 is negative 16 minus 1. Definitely get a negative here. I will get a negative here. when I get numbers bigger than 1/2, like 1. 2 times 1 minus 1 will be positive there. For the 7, I plug in numbers like -8, I get a negative here, but anything bigger than -7 is going to be positive. What goes in this first blank right here? Positive. Be careful, because that one's weird. Where it's backwards, it starts with the positive, right? Because if I plugged in -8, I'd have 3 minus -8, which would be positive 11, right? So positive, positive, positive. When you plug in numbers bigger than 3, then you'll have like 3 minus 4. That's when you get the negative. And then you're just looking to see even or odd. So we've got even right here, so that's positive, negative, positive, negative for that. And I'm going to go right here on this axis. I'm going to put an X on that 3 to remind myself that my value cannot equal 3, because I'd put a 0 in the denominator. It's going to matter a little bit on this. This one's looking for greater than or equal to 0. Is that positives or negatives? Positives, right? So I'm going to do positive, positive. Those are my answers. Now, it's or equal to, so I need to use brackets. So I would do negative infinity, which I'm going to use a parentheses there, because you always have to use a parentheses with the infinity. Can't actually get there. But with -7, I will use a bracket. And then from 1/2 to 3 is going to be my next part. I use a bracket with 1/2. Can I use a bracket with 3? I can't have a 0 in the denominator, so I'm going to put a parentheses there. If it doesn't have that or equal to sign, it really doesn't matter if you pay attention to that, because you're going to have all parentheses anyway. But if it has the or equal to sign, to be 100% correct, you need to make sure that you have a parentheses with that 3.
The smallest number comes first, right?
Smallest number comes first, always, yes. On a multiple choice question, unless they're really being cruel, they're probably not going to give you this and then another one where it's all brackets. So multiple choice, you probably won't have to pay that close attention to it. On a free response question, that parentheses versus a bracket could be the difference in getting like a point on that. So you want to be careful. Okay, questions? All right, now I have to see. I'll pass this out while I try to make my decision. Do number 1 and number 5 on this worksheet. So, on this worksheet, do number 1 and number 5 for me. When you get it done, check with your neighbor and see if you're getting the same thing as them. Okay. Here are the answers to these. So let's check and see how we're doing. Number 1, you should get 0, 2, and negative 3. Those are your answers. The 4 and the negative 2 are your excluded values. They don't conflict with any of your answers. You need to consider them, because if you had like an x cannot equal 2, you'd have to throw an answer out. But 0, 2, and negative 3 are the answers. And then for number 5, you should get negative infinity to negative 7 with parentheses, and then negative 2 to 5, where you got a parentheses with negative 2, a bracket with 5. Okay, so if your problem has just a less than, which is actually all the rest of them on this page, right, then you don't have to worry about it. You're just going to use parentheses with everything because it's not equaling 0, so just parentheses all the way across. This one does have an or equal to, so you have to think about it. So notice when I did this, in the top I got x equals 5. In the bottom, I got x cannot equal negative 7, and x cannot equal negative 2 because we can't have zeros in the bottom. So when I did my line, I put an x on top of those to remind myself I can't put brackets with those numbers, right? So what you want to do for this, when you're doing your answers, you really should use brackets with everything because it's or equal to, but negative 7 and negative 2 are in the bottom. So you can't use brackets with them. You have to use parentheses.
Whatever numbers are closest to like intercrossing 0.
No, it's whichever numbers came from the bottom of the fraction. So this x plus 7 gave us negative 7. So you can't have a 0 in the bottom. Negative 7 plus 7 will give you a 0 in the bottom of that fraction. So it's still like a boundary point where you're going to switch from positive to negative, but you can't equal that number. So you would not use a bracket with negative 7. Same thing for negative 2. Negative 2 plus 2 would give us a 0 in that bottom. It came from the bottom. So you cannot use a bracket for it. 5 is okay because it came from the top. You can have zeros in the top. You cannot have zeros in the bottom. And again, you only have to consider it if there's an or equal to sign there anyway. If it's a less than or a greater than sign, you just parentheses for everything. Yes, it will be multiple choice. So it's unlikely that I would give you answer choices where the only difference is the parentheses and the bracket at this point. So if you got the main idea and are still just a little shaky on the parentheses and brackets, you'll probably still be okay tomorrow for that. Okay, now I was going to assign this to you as the assignment last night, but of course we have ran out of time as always because that is the story of my life. So I am not going to assign the rest of that to you. However, if you feel like you need some more practice with it, it's posted on Canvas. The answer key is up, so you can do it and check your work if you feel like you need a little bit more work with it. Okay, but if you feel pretty good, this stuff will be on the quiz. It will be fairly basic what you're going to see. It'll be questions like you see right there. It won't be anything too crazy. All right, so let's switch over to those notes I passed out to you. They're short, so maybe we can do it. Hope. And we are on this. Okay. All right. I don't even know what this is or where it came. Oh, I do know. It came from here. Oops, it's over here somewhere. Okay. All right. So I'm using Mr. Passwater's notes again. They're a little bit wordy, but they are helpful. It goes over what a rational function is again. It's a polynomial on top and bottom. Since we are dividing by polynomial, rational functions have restrictions on their domain. We just talked about that. Those are the numbers we can't have in the bottom, right? So g of x cannot equal 0. now what I want to do is talk about what happens at those points. We know we can't have a 0 in the bottom. We want to describe specifically what is happening at those points. And at those points, you're going to have either a hole in the graph or a vertical asymptote. Okay? A hole is going to occur when the factor in the denominator cancels out with factors in the numerator. And a vertical asymptote is going to occur when a factor in the denominator does not cancel out with the factors in the numerator. So, here is an example. Here we have, this is factored for us right here. Notice that there is an x minus 1 in the top and an x minus 1 in the bottom, right? So, those two right there could cancel each other out. You're still going to have a discontinuity at x equals 1, but it's just going to be a teeny tiny hole in the graph. For example, I'm going to flip over to Desmos real quick and graph that. Desmos. And if I graph y equals x plus 1, x plus 2 over x plus 1. Alright, x cannot equal negative 1, right? That would give us a 0 in the denominator. But if I look at negative 1 right here, I don't see a problem, right? It just looks like a line to me. However, you don't get to use Desmos anyway, but if I were to drag, oh, there it was. Did you see it? It was so fast, right there. If you drag it along to negative 1, there's a hole in the graph right there. So you can't have the point there of negative 1. But everything around it is perfectly fine. Okay? So that is what a hole looks like on the graph. Sometimes it will be given to you like he has shown in the graph here, where they're going to represent it just by a little open circle right there. It also can happen, like for example here, I've got x minus 1 to the third power and x minus 1 to the second power. What that means is I've got x minus 1 times x minus 1 times x minus 1 on the top, and I've got 2 times x minus 1 times x minus 1 on the bottom. So this would cancel out with this one would cancel out with this one. I would still have an x minus 1, but it would be in the top. So all the x minus 1s in the bottom have canceled out. So that would also have a hole at x equals 1. Yes? The x minus 1 on the top, you had one x minus 1 on the top that did not cancel, and then just the number 2 is left on the bottom. Okay? However, if we have zeros in the denominator that do not cancel, so, for example, x minus 3, x plus 2, x minus 1, nothing cancels there, right? We are going to get a vertical asymptote. So a vertical asymptote is going to look something like this on the graph. It's going to be a line that you get closer and closer and closer and closer to as you approach that value. So like for example here, x, this would be at x equals positive 1. And so if we think about that graph right there, x equals positive 1, that vertical line, we're getting closer and closer and closer to it, but we never touch it. These are much easier to see from a graph. If you're graphing it like on the calculator or Desmos, you can see this happening. On the calculator or Desmos, holes don't show up. Now, if they give you a graph, they'll put an open circle at the hole. But if they're asking you to graph it on the calculator's not going to show you where the hole's at. It's also true here. Notice this is similar to what we saw over here, but this time we've got x minus 1, x plus 2. Oh, it's doing this crazy thing again. And then we've got x minus 1 and x minus 1 over here. It's creeping down the page there. So this time, this one would cancel, right? But I would still have an x minus 1 left in the bottom. So if you have an x minus 1 left in the bottom, you have like a hole and an asymptote at the same place, but the asymptote is always going to trump the hole. It's always the bigger feature, right? So you would still have a vertical asymptote at x equals 1 for that. Okay, so if they cancel, it's a hole. If they do not cancel, asymptote, right? That's our main thing that we need to know. Now, here is some notation that we have to use, okay? And this is the thing that's different from how I've taught this before. I've not had to do limit notation, but it appears limit notation for this may show up on the AP exam. So right here, this says limit as x approaches. I hate this. Okay. It's like I need to teach you about limits before I teach you this. But, all right, this one says limit as x approaches 1, and it's got a minus sign behind the 1. We don't ever put minus signs behind the 1, right? So what this means right here is x approaches 1 from the left. Okay, so if you see a plus or a minus sign behind a number, that is telling you it's either from the left or from the right. And so over here where we've got that 1 with the positive behind it, it is telling us x approaches 1 from the right. Okay, so here's what's happening. Right here is where x equals 1 on this first graph, correct? So if I trace this graph from the left side, if I start over here, I go down here, I jump back up here. As I go from the left, I get closer and closer and closer to that point. Do I ever actually get there? No, because there's a hole in the graph right there, right? I can't get there, but I'm getting close to it, right? So a limit doesn't tell us what the value equals, but what we're approaching. And we are approaching that point right there. And from the right side, we also approach that same point, right? We don't ever get there because of the hole, but we're approaching that point. And what is the y value of that point? And for some reason, it won't let me draw on this, and it's driving me crazy. But that is 3, right? Even though it went down. So we get 3 for those answers right there. Now, this is the same thing over here. The limit as x approaches 1 from the left and the limit as x approaches 1 from the right. On this case, 1 is right here. It's this vertical asymptote, right? So as we get closer and closer and closer to that vertical line from the left, where are we going? Down and down and down and down and down. That's negative infinity, right? And then from the right, we would go up and up and up and up and up and up and up. That'd be positive infinity for that. So at vertical asymptotes, you should have positive or negative infinity for those answers. At hole, you're going to have the y coordinate of where that would be for that. I don't think they'll ask you that from anything but a graph right now. Hope. We'll see for that. So, determining holes and asymptotes, to me, is not that difficult at all. The limit notation is going to make it a little bit more difficult. So, especially if they're already factored for you. If they're already factored for you, if we look at A, it is already factored, right? Holes and vertical asymptotes are the values you cannot equal. They come from the bottom. So you're going to look at the bottom, right? And I know that I'm going to have something at x equals negative 3, and I'm going to have something else at x equals positive 5. I have something there because it's going to give me a 0 in the bottom, okay? One of these is going to be a hole. One of them is going to be a vertical asymptote. Which one is the hole? It's the negative 3. Why, Tyler?
Because they cancel out.
Because those factors cancel out. So that is your hole in the graph. And I don't know if he uses this wording, but let me also tell you up here, a hole is also sometimes called a removable discontinuity. Okay, a discontinuity is just a place in the graph that you have, like you'd have to pick up your pencil if you were tracing it. This is called a removable discontinuity because you could fix it with one single point. All you would have to do is put one point there, and then it would be continuous again, right? So in case you see that wording, I know in calculus we use that a lot. I don't know if they're going to use it in pre-cal or not, but it could show up. Holes and removable discontinuities are the same thing. And then here is our vertical asymptote.
Just the opposite of whichever is a hole.
They can both be holes or they could both be vertical asymptotes. What matters here for this, Lucas, is whether or not it cancels with anything in the numerator. So the x plus 3 canceled with the x plus 3 in the numerator. That's how we knew we had a hole there. The x minus 5 does not cancel with anything in the numerator, so it's a vertical asymptote. But sometimes you have all of them are vertical asymptotes. Sometimes they're all holes. Sometimes you have a mixture. It just depends on the problem.
Can you have a vertical asymptote and a hole at the same number?
It can happen, like theoretically, but if you have a vertical asymptote and a hole at the same number, it is a vertical asymptote for that. So like on this one, on this one, you only look at the bottom, right? The top gives you your zeros. The bottom's where you find those discontinuities, holes and vertical asymptotes. So we got x equals 2, and we got x equals -1, right? For x equals -2, it might even be helpful on this to write this out. This is x plus 1, x minus 2, x minus 2 over, and then we'll have x minus 2, x plus 1, x plus 1, right? So if we think about what that means. So at the 2, this 2 cancels with the 2 in the top. We still have a 2 left, x minus 2 left, but it's in the top, right? So what's in the bottom has canceled out. So this is going to be a hole. Okay. Then if we look at our x minus 1, that goes with this x plus 1. One of them cancels, but we still have one left in the bottom, right? So this is where you're talking about you have a hole and an asymptote in that case, but the asymptote is like more powerful than the hole in all cases. So this one's going to be a vertical asymptote. I don't mind if you put VA on your homework, but just know what it stands for because it'll be written out on a quiz or test.
So basically, whichever is first on the bottom.
If when you cancel, if it's still left on the bottom, it's a vertical asymptote. If it cancels out and is not on the bottom anymore, then it's a hole. So like this x minus 2 right here, when I canceled with it, I didn't have any more x minus 2's in the bottom. So that was a hole. And then like here, this one canceled, but I still had one left here. So that's what made it a vertical asymptote instead of hole. Okay. All right. C, we have 1 over x cubed plus 4x. Can't do anything with the top. How do I factor that bottom?
First, you have to take out an x.
Take out an x, and then I'll have what will be left on the inside.
Square root of 1.
Can I factor that?
Yeah.
Are you sure?
Oh, wait.
I got numbers that got to multiply to give me 4, which would be either positive 2 and positive 2, or negative 2 and negative 2, or positive 1 and positive 4, or negative 1 and negative 4, or any of those going to give me 0, not with the same signs, right? So for that to factor, it'd have to be a -4, and then it would factor. That won't factor. Let me erase that right there. Oh, wait, no. Right here. So let's erase this right here because it's taking up too much room. So I have x equals 0 is something. Actually, is anything going to cancel with a numerator? Nothing is going to cancel with the numerator because there's nothing in the numerator, right? So everything here is going to be a vertical asymptote. Nothing cancels in the bottom. So that's a vertical asymptote for sure. And then I've got x squared plus 4. So I want to look at where x squared plus 4 equals 0. It wouldn't factor. I would have to subtract that 4, so I'll get x squared equals negative 4, and then I will try to square root both sides. But what is square root of negative 4? Can you take a square root of a negative number? Is there any number times itself that will give you a negative number? There is not. You can't take square root of a negative, so you don't actually get an answer from that. That value is always positive. X squared is positive. You're adding 4 to it, which makes it even more positive. So you don't have a vertical asymptote from that part. So it'll always have probably like a square or something for that to happen, but it can happen where you have a piece that doesn't give you a asymptote. There. So just a vertical asymptote is 0 for that one. Okay, so let's do this, and ask us to write a left and right limit statement as x approaches 2 for each of the following functions. So I'm going to write the limit statement here before I even think about what it would be. So I have limit, and we're looking at x approaches 2 is what it's asking us to look at. And from the left, I would put a little minus behind that 2. And that tells me I'm approaching that vertical line x equals 2 from the left side. And then you always want to put f of x right here, or whatever the function is named. You know, on the next one it's going to be g of x, on this one will be h of x here. And then we're going to put an equal sign. So that's what our limit notation is going to look like. For the right-hand side, we're going to do the same thing, but we'll have a little positive behind of our 2 right there. So that's what your limit notation looks like for this. All right, so for this, write a left and right limit statement as x approaches 2 for each of the following. We've got to think about first of all, whether it's a whole or vertical asymptote. If it's a whole, we'll get a number for these answers. If it's a vertical asymptote, we're looking at positive and negative infinity. Do we have a vertical asymptote or a whole? There's no whole because nothing cancels. At x equals 2, because that comes from the bottom, right? We've got a vertical asymptote. That tells me that this graph, whenever I get over here to 2, I've got like a dotted line right here, and I'm going to either approach positive infinity or negative infinity. So, what we want to think about here is what, there's a couple ways I could teach you to do. Let me look back at his, hold on, sorry. Let me look at his real quick, because what I'm thinking of telling you to do is going to take too long. Let me see if there was a shortcut he used. Okay, yeah, let's do that. Okay, here's what he does. He just picks a number really close to 2 to see whether you're getting like positive or negative values. It's a little dangerous because if you don't pick a number close enough to 2, it might not work. But probably if we like plug in 1 right here to see what we'll get, we would, one's not going to be great. One's going to give you 0, isn't it? Well, 1's not great to use. Let's go closer. Let's do like 1.5, right? So a number like, or maybe even like 1.9. Right? 1.9 is really close. If I do 1.9 minus 1 times 1.9 plus 3 over 1.9 minus 2. I really don't care about whether or not this is what number this is. I care about whether we're going down to negative infinity or up to positive infinity, right? So 1.9 minus 1 is a positive number. 1.9 plus 3 is a positive number. 1.9 minus 2 is a negative number. What will I get overall for that? negative. That was going to be negative. So this side, I'm not really sure what it looks like, but it's going down. So on the left side, as we approach from the left side, we've got negative infinity. And then,
How does that make it, how do you know that's for the left side?
because 1.9 is lower than 2. Yeah, so we're picking a number lower than 2 to plug in, so that's coming from the left side. So what should we pick to plug in for the right side? Like 2.1 would be great. So if we do 2.1 minus 1 times 2.1 plus 3 over 2.1 minus 2, then we would get a positive, and on the bottom also a positive. So since we're getting a positive number there, this side is probably going up right there. So we get a positive infinity from the right side. Okay, we're out of time today. So